Hey there guys, this is part 2 of my walkthrough through AQA's Higher GCSE Physics, Specimen 2018, Paper 2. Part 1 seems quite popular, so my adventures through science can continue. If there's any particular science content you want to see on the channel, let me know down below in the comments. So here, we're kicking off at question 7. You can get the paper down below in the description, as well as part 1 and the formula sheet. Let's do this. Okay, question 7. In 2011, some of the scientists working at the CERN Particle Laboratory published results from experiments conducted over the previous 3 years. Their results suggested that a particle called a neutrino was able to travel faster than the speed of light. These unexpected results challenged the physics theory that nothing can travel faster than the speed of light. 7.1 wants us to suggest why most scientists found these results to be unbelievable. So, it is a widely believed and respected idea that nothing can travel faster than the speed of light. That comes from our boy Albert Einstein. Theory of relativity shows this to be true. That theory is now over 100 years old. There's plenty of experimental data in support of the theory, so most scientists have come to believe that it is absolute fact that nothing can travel faster than the speed of light. So when a new theory comes along and suggests actually there is this new particle that can travel at the speed of light, they are definitely thinking, that seems fishy, because that goes against everything that we have come to believe. Also, the theory that nothing can travel faster than the speed of light is the basis of so many working physical theories and ideas out there as well. So if this neutrino came along, travelled faster than the speed of light, that's going to naff up quite a few theories and ideas. 7.2. The scientists at CERN believed their results to be correct, but could not explain them. We want to suggest 2 reasons why they published their results. So the first one I thought of was to show that they have actually been doing some work and they've actually got some results from all these experiments that they are doing. Secondly, I then thought, well, they've got these weird results, so if they publish them, other scientists out there can analyse and process the data and see what they make of them. So peer review, it might encourage other people out there to do their own experiments, see what data they get, anything along those lines, and we'd be golden. 7.3 says the experiments conducted by the scientists involved measuring the time it took for the neutrino to travel from CERN to another laboratory 730,000 meters away. Using this data, they measured the speed of the neutrino to be 300,007,400 meters per second. Our mission is to calculate the time it would take the neutrino to travel 730,000 meters at 300,007,400 meters per second, giving our answer in standard form. So, speed is distance over time. We want time, so from that we can get our speed times time is distance, and then if we divide through by speed, we get time is distance over speed. So the time is going to be 730,000 divided by 300 million 7,400. Now if you put that into your calculator, you should get the answer in standard form. Mine did, so hopefully yours will too. So if we go to 2 decimal places, we get 2.43 times 10 to the minus 3, and that is seconds. Cool. 7.4. In 2012, the scientists realised that the unexpected results were due to a timing error. This error meant that the time recorded was always 16 nanoseconds less than the actual time. Which of the following is the same as 60 nanoseconds? Okay, so 1 nanosecond is 1,000 millionth of a second. So it's 1 over 1,000 millionth of a second, which is 1 times 10 to the minus 9. So 60 nanoseconds then is 60 times 10 to the minus 9. So there's our guy. 7.5 asks, what name is given to this type of error? So the error happened not because of chance, but because of problems in the measurement process. So this type of error is called a systematic error. 7.6 then wants us to suggest what the scientists should do to get an accurate value for the speed of a neutrino. So all of their recorded times are 16 nanoseconds less than they should be. So what they should do is add 60 nanoseconds to each of their recorded times and then calculate the speed. Question 8. A train travels from town A to town B. Figure 14 shows the route taken by the train and is also drawn to scale. So there's figure 14. Part A says the distance the train travels between town A and town B is not the same as the displacement. We're asked, what is the difference between distance and displacement? So, distance just tells us how far away from an object we are. Doesn't tell us anything about what direction we are from where we started. Displacement tells us how far we are from where we started and in what direction. So, displacement is a vector because it has size and direction or magnitude and direction. Distance only has size, so it's not a vector, but it is a scalar. It's the same sort of situation as speed and velocity. Speed only tells us how fast we're going, velocity tells us how fast and in which direction. Again, because velocity is a vector, speed is only a scalar. Then 8.2 says to use figure 14 to determine the displacement of the train in travelling from A to B. Show how we get our answer. So here then they want the displacement and the direction. So for the displacement part we want to determine the straight line distance between A and B. So if we draw a straight line between A and B, you would then want to measure it, and you should get 7.5 centimetres. So we then use the scale. 1 centimetre represents 5 kilometres. So we do 7.5 times 5 kilometres, and that gives us 37.5 kilometres. So that is our displacement. And then for the direction, we need the bearing of town B from A. So at town A, we want to draw a north line in. North, remember, is 0 degrees. And then we would measure this angle, which would give us 62 degrees. As a bearing then, bearings are usually 3 figures. It would be 062 degrees. 8.3 says there are places on the journey where the train accelerates without changing speed. We want to explain how this can happen. So, if we look at the route the train takes, it's definitely not a straight line. So that means there are places on the journey where the train changes direction. Now a change in direction means a change in velocity, and acceleration is the rate of change of velocity. So when the train changes direction, its velocity changes, meaning its acceleration changes, but not necessarily its speed. 8.4, figure 15 shows how the velocity changes over a straight section of the journey. So we've got velocity going up the side in meters per second, time going along the bottom in seconds. So we are asked to estimate the distance travelled by the train along the straight part of the journey, shown in the graph. To gain full marks, we must show how we get our answer. So we have a velocity time graph. Distance on these guys is the area under the curve. So, it does say a magic word, estimate. Let's first of all work out how much each square is worth. So each square is 5 high and 100 wide. So each square is 5 meters per second times 100 seconds. So the seconds cancel out and give us 500 meters. So each square represents 500 meters travelled. So now we need to work out how many squares we're going to use. So it's only an estimate. Okay, so we got 5 whole squares along the bottom, pretty much 3 whole squares in the next row, so that's 8, 2 whole squares in the next, so that's 10, 2 whole squares above, so that's 12, another 2 above that, so that's 14. Now we should probably take this one because it's almost whole, so that's 15. If we take this one and this one as one square, that's 16 squares, and then we'll have this one as well because it's almost whole. So I'm going to say that we got 17 squares. So we're then going to do 17 times 500 meters, and that's going to give us 8,500 meters. Cool. Okay, question 9. The stopping distance of a car is the sum of the thinking distance and the braking distance. Table 4 shows how the thinking distance and braking distance vary with speed. So there's our table times 9.1 asks what is meant by the braking distance. So when you apply the brakes in a car, you do not stop instantly. You do carry on travelling a little bit until you stop. When you apply the brakes though, you are applying a braking force to the car. Braking distance is the distance you travel under the braking force. So it's the distance you travel between applying the brakes and stopping. 9.2. The data in table 4 refers to a car in good mechanical condition driven by an alert driver. We want to explain why the stopping distance of a car increases if the driver is very tired. So, if you are tired, you are not going to be as alert as someone that's not tired. So that means your reaction time is gonna be longer. If your reaction time is longer, that means there's a greater period of time between thinking about applying the brakes and actually applying the brakes. That means your thinking distance is going to be greater. So if our thinking distance is greater, then our stopping distance, which is thinking distance and braking distance, is also going to be longer. Okay, 9.3. The student looks at the data in table 4 and writes the following. Thinking distance is proportional to speed and braking distance is proportional to speed. We want to explain whether or not the student is correct. So, when two things are proportional, so these would be directly proportional here, it means as one of the things is affected by a factor, then the other thing is affected in exactly the same way by the same factor. So for example, if we look at thinking distance and speed first of all, then if they are directly proportional, as speed doubles or triples, then thinking distance would double or triple. So let's have a look. Okay, so when the speed is 10 meters per second, thinking distance is 6. If we double the speed to 20, the thinking distance doubles to 12. If we were to triple the speed from 10 to 30, then our thinking distance goes from 6 to 18. So, speed and thinking distance are directly proportional. So, just going to call it TD. Thinking distance and speed are directly proportional. If you like, you could put in an example there to back that up. So you could say when speed is 10 and then doubles to 20, thinking distance goes from 6 to 12. So let's see if the same thing works for braking distance. So, if we go from a speed of 10, then we have a braking distance of 6. If we double our speed to 20, then our braking distance is 24. So that is not 2 times 6, that's actually 4 times 6. So speed and braking distance are not directly proportional because they are not affected in the same way by the same factor. So then we would say that speed and braking distance are not. So again, you could put an example there, the one that we've just gone through, and say that if we double 10 to 20, we don't get double 6. So, is the student correct? No. Applying the brakes with too much force can cause a car to skid. The distance a car will skid before stopping depends on the friction between the road surface and the tyres, and also the speed of the car. Friction can be investigated by pulling a device called a sled across a surface at a constant speed. Figure 16 shows a sled being pulled correctly and incorrectly across a surface. The constant of friction for the surface is calculated from the value of the force pulling the sled and the weight of the sled. So here's our diagram. So the sled is the rectangular bit. We've got a piece of tyre rubber on the bottom making contact with the surface, and if it's being pulled correctly, we can see it's being pulled exactly horizontally. If it's being pulled incorrectly, then it's being pulled upwards and along. Okay, so we are asked, why is it important that the sled is pulled at a constant speed? So it's multiple choice. There are our answers. So let's think about this. The friction is calculated from the force pulling the sled and the weight of the sled. If the sled, or whatever was pulling the sled, was accelerating, and remember, force is mass times acceleration. So if the speed is changing, then the force pulling the sled is changing. So that will mean if the sled accelerates, the value for the constant of friction will be wrong, because we won't get a constant value. It will change because the force will change. 9.5. If the sled is pulled at an angle to the horizontal surface, then the constant of friction calculated would not be appropriate. Explain why. So now we're looking at this situation. So the force here, the pulling force, is not just horizontal. So the pulling force has two components. So pulling force would have a horizontal and a vertical component. Now let's think about what these components are going to do. The horizontal force is going to pull it along, so that's no problem. The problem is the vertical force. So the vertical force, or the vertical component, well, what's that going to do? It's an upward force, so effectively it's going to lift the sled upwards, reducing the force between the sled and the surface. So the vertical component pulls the sled upwards. Reducing the force between the sled and the surface. So that would completely bugger up the reading or the calculation for the constant of friction. Okay, 9.6. By measuring the skid marks, an accident investigator determined that the distance the car travelled between applying the brakes and stopping was 22 metres. He then investigated the friction using a sled and was able to determine the car decelerated at 7.2 meters per second squared. We want to calculate the speed of the car just before the brakes were applied, giving our answer to two significant figures and using the correct equation from the physics equation sheet. So, what do we know? We know the distance travelled, we know the deceleration would have been minus 7.2 meters per second squared because it's deceleration. And we also know final velocity is 0. So the formula that we want to use is this guy. Final velocity squared minus initial velocity squared is 2 times acceleration times distance. So our final velocity is when we have stopped. So that is 0. So we're going to get minus initial velocity squared. Initial velocity is u. So we get minus u squared is equal to 2 times acceleration. So because it's deceleration, that's minus 7.2. So we got 2 times minus 7.2 times 22. So on the right hand side we are going to get, well, we're going to have minus u squared is equal to minus 316.8. Now because both sides are negative, we can cancel that out and make both sides positive. So we get u squared is 316.8. So u is the square root of 316.8, which gives us 17.79 blah blah blah. So that's meters per second. Two significant figures. While the second sig fig is the 7 in the 17, we got 0.7 after it, so that's going to round up to 18 meters per second. Good times. Lesson 10 is all about atmospheric pressure. So figure 17 shows how atmospheric pressure changes with altitude. So we got our atmospheric pressure going up the y-axis in kilopascals and altitude going along the bottom in kilometers. So we can see we have an inverse proportion relationship here. As altitude increases, atmospheric pressure decreases. 10.1 wants us to explain why atmospheric pressure decreases with increasing altitude. So it's 3 marks, so we need to say really 3 things. So first of all, what makes pressure? What causes pressure? Well, pressure is caused by molecules colliding or hitting a surface. So atmospheric pressure is caused by air molecules hitting a surface. So that would be the first thing that we want to say. Now, as altitude increases, air gets thinner. So that means there are less air molecules the higher up we go. It's why helicopters can only fly so high. If they try to go any higher, the air is too thin. They can't apply the the upward force that they need to against the air molecules. So helicopters can only go so high. So the higher up we go, the less air molecules there are. So as the number of air molecules decrease, so too then does the number of air molecules hitting a surface. So if there are less air molecules colliding with a surface, then there is less pressure. Cool. Okay, 10.2, we got a 95 marker here. So when flying, the pressure inside the cabin of an aircraft is capped at 70 kilopascals. The aircraft window has an area of 810 centimeters squared. We want to use data from figure 17 to calculate the resultant force acting on an aircraft window when the aircraft is flying at an altitude of 12 kilometers, giving our answer to two significant figures. So a resultant force is the difference between any forces acting on an object. So the aircraft window is going to have two forces acting on it. It's going to have a force from the inside, which we'll call the internal force, and a force from the outside, which we'll call the external force. So we need to calculate both of these forces and then find the difference between them. So the first thing we're going to need is the good old formula: pressure is equal to force divided by area, where force is in newtons and the area is in meters squared. So, if we rearrange that formula, we can get force is pressure times area. So, at the moment, the area of the window is in centimeters squared. We need to change that into meters squared. Now, I know from maths, turning centimeters squared into meters squared can be a bit tricky. So, let's just draw ourselves a rectangle with an area of 810 centimeters squared. So we could have one length of 1 centimetre, which would mean the other length would have to be 810 centimetres. Now if we convert these to metres, divided by 100, 1 centimetre is 0.01 metres, 810 centimetres is 8.1 metres. So obviously these aren't going to be the actual dimensions of the window, but it's a model that works. So we can now work out the area of the window in meters squared. So the area is 0.01 meters times 8.1 meters, which is going to give us 0.081 meters squared. Cool. Okay, we can work out the internal force. So we know that the internal force is going to be, well, the internal pressure is 70,000 pascals. Sorry, yeah, 70,000 pascals, because it's 70 kilopascals. So we got 70,000 times the area of the window, that's 0.081 0.081, and that is going to give us an internal force of 5,670 newtons. So that is the internal force acting on the window. We now need to work out the external force. To do that, we need to work out the pressure. So if we're flying at an altitude of 12 kilometers, we need to go to our graph. Okay, so the scale going along the bottom is a bit mental. Every 5 little squares is 2. So we got 2, 4, 6, 8, 10, and then 12 here. So we go up till we hit the graph, which is there, and then across to get our pressure. So our pressure is 20 kilopascals. So the pressure at 12 kilometers is 20,000 Pascal. So we can work out the external force. It's 20,000 times 0.081, and that is going to give us 1,620 newtons. So the resultant force is the difference between these two forces. So the resultant force is 5,670 minus 1,620, and that is going to give us 4,050 newtons. Now the question wanted it to 2 significant figures. So the 0 between the 4 and the 5 is our second sig fig. It has a 5 after it. So we're going to round up to 4,100 newtons. Cool. At 10.3, we got the cross section of one type of aircraft window. So we got a higher pressure inside the cabin and a lower pressure outside the cabin. Now we can see that the window is going to have a larger surface area inside the cabin than outside the cabin. We want to explain why it has been designed like this for 2 marks. So we've just seen up above that the force acting on the window from the inside is bigger than the force acting on it from the outside, because the pressure inside is higher than the pressure outside. So believe it or not, the force acting from the inside is trying to push the window out of the aeroplane. Now obviously we don't want that to happen, that would be a really bad day. So designing it like this stops the window from popping out and then there being a big hole in the side of the aeroplane and everything being sucked out of it, because that would be really bad. Question 11. Waves can be either longitudinal or transverse. 11.1 for 2 marks wants us to explain the difference between transverse waves and longitudinal waves. So, waves transfer energy from one point to another. Transverse waves well, their oscillations are perpendicular to the direction of energy transfer. So examples of this are light waves, infrared, X-ray, and waves in the water. So on the flip side, longitudinal waves have oscillations that are parallel to the direction of energy transfer. So an example of longitudinal waves are sound waves. 11.2 wants us to describe one piece of evidence that shows when a sound wave travels through the air, it is the wave and not the air itself that travels. So, if the air itself was travelling, then anything that emits sound waves would cause a vacuum to form around that thing. So, for example, we could say, well, a vacuum does not form around a loudspeaker. So that shows that the air does not travel, it is the wave. The air does move. Molecules either move closer together or further apart, causing compressions or rarefactions, but the air does not travel, it is the wave. Okay, 11.3. So we've got a diagram of part of a moving coil loudspeaker. A coil of wire is positioned in the gap between the north and south poles of the cylindrical magnet. So there's our diagram. So we've got a permanent cylindrical magnet. We've got a coil of wire wrapped around the core of the magnet. We've got leads that carry a current to an electrical circuit, and we have a paper cone. We are asked to explain how the loudspeaker converts a current in the electrical circuit to sound waves, and it's a big 6-mark question, so we need to be really thorough and go through the whole story. Okay, so first of all, the current flowing to the electrical circuit has to be varying, so it has to be an AC electric supply. Now the current in the electrical circuit will flow through the coil. The coil is wrapped around the core of the magnet. So when the current flows through the coil, that is going to produce a magnetic field. The magnetic field of the coil is then going to interact with the magnetic field of the permanent magnet. When these two magnetic fields interact, it's going to produce a resultant force. So this force is then going to act on the coil. The coil is either going to move left or right, depending on whether the magnetic fields attract or repel each other. Now, when the current is varied or switched, then the force will be reversed. So if at first the coil moved left, switch current, and it's now going to move right. So what this is going to do, these movements are going to make the coil vibrate. The size of the force, the power of the vibrations, would depend on the size of the current. So if we had a greater current, we're going to have a greater force, we're going to have stronger vibrations. Now the vibrations from the coil make the paper cone vibrate. when the paper cone vibrates, it's going to make the air molecules inside the paper cone vibrate, which is going to nudge some of them closer together and others further apart. So what that's going to do is create compressions and rarefactions inside the paper cone, creating sound waves. That's how it works. You would want to get down a nice, coherent, logical flow like that to get all 6 marks. Okay, question 12. We're looking at a piece of apparatus called a current balance. So we're told when the switch is closed, the piece of wire labelled X experiences a force and moves downwards. 12.1 asks what name is given to this effect. So the wire over here is inside a magnet. When a current passes through the wire, we create a magnetic field around the wire. So the reason the wire moves downwards is because the magnetic field around the wire is affected by the magnetic field from the magnet. This is called the motor effect. 12.2 asks us to suggest one change we could make to the apparatus so that the wire at X experiences a greater force. So to experience a greater force, we would need bigger magnetic fields. So either increase the strength of the magnet or increase the current flowing through the wire. That will then increase the strength of the magnetic field around the wire. Final question, we got quite a big one. So we're now shown that a small weight has been put on the insulating bar so that wire X goes back and balances at its original position. Now we can see the distance between X and the pivot is 8 centimeters. We're told the wire X is 5 centimeters long and the current passing through the wire is 1.5 amps. We're told the small weight causes a clockwise moment of 4.8 times 10 to the minus 4 Newton meters. And we are asked to calculate the magnetic flux density where the wire X is positioned, giving the unit and its 6 marks. So the formula that we need is given to us. It's this guy. So force is magnetic flux density times the current times the length. Now the length is the distance between X and the pivot. We know the current. We know, well, actually, we don't know the force, so that's a bit of a problem. So we can work out the force though, because we know the moment. Now the moment, so a moment is force times distance from pivot. Now we're going to want that in meters. So 8 centimeters is 0.08 meters. Okay, so we know the moment is 4.8 times 10 to the minus 4 Newton meters. So we know that's equal to force times 0.08 meters. From that, we can get that the force is 4.8 times 10 to the minus 4 Newton meters divided by 0.08 meters. Now that gives us a force of 0.006 newtons. So we now know our force is 0.006 newtons. Okay, so now that we know the size of the force, we can start playing around with the formula. So let's first of all make it a bit nicer. Force F is equal to magnetic flux density B times current I times length L. So we know 0.006 is equal to B times 1.5 times, well, the length is 5 centimeters. We need that in meters, so it's 0.05. So that gives us 0.006 is equal to 0.075 B. So if we divide by 0.075, we get B is 0.006 divided by 0.075. Now that gives us 0.08. So that's the number. As for the unit, magnetic flux density is measured in Tesla. So, there we go guys, paper done. So, this whole thing was a bit of an experiment in true nature of science. If we want more science content, let me know. Hope you found this useful guys.